All right, so today we're going to talk a little bit about circuits. So to get us started, let's just do a quick little review. Your circuit must consist of some sort of voltage source. So this little two-line symbol right here represents my battery. It's two lines of different lengths to represent the high and low voltage ends of the batteries, or positive and negative end of the battery. If you're looking at a physical battery, that's what you're used to seeing. And so in order for my electrons to want to move, in order for me to have that electric current or flow of electrons, we have to have a potential energy difference, meaning we have to have a difference in the amount of potential energy available. And so that's what this voltage source or battery does for us. It provides one end of the battery with a different amount of potential energy than the other, so that the electrons then want to move in an attempt to try to balance that out. Now, the electrons have to have some sort of pathway for them to travel through, and we're going to go ahead and draw our circuit today so that it has some sort of device for the electrons to turn on as they flow around. Okay, so we have our electron here with, our circuit here with some sort of wire coming out of the positive end, and then we'll have a wire connecting it to the negative end. And our device is going to have a pathway here connecting it to our voltage or our battery source. Now, I'm going to go ahead and draw us a light bulb. And so that light bulb would essentially connect the circuit so that we have a closed circuit. So remember that you must have a pathway all the way around from high to low, positive to negative, in order for the electrons to move. So as long as this circuit is complete, this device will turn on, okay? If for some reason we have some sort of break, gap, opening in our circuit, well, now this is no longer a complete circuit, and so this device will no longer work, okay? If we have a device that's attached to some sort of circuit with a switch, if that switch is open, that is a break in the circuit. The device will no longer work, all right? If we have a device that has a complete circuit here, and maybe we have a circuit with, let's draw a different one here. Maybe we have a circuit and it has more than one device. If one of these devices were to go out, so let's say that, right now it's all working, and then something goes wrong and this device over here burns out. Well, guess what? If that device burns out, if it's broken, if the filament has burned so that there's no longer a connection, then you might as well have just taken that device completely out and left yourself a gap, because that is basically what happens. That burned out device creates a gap in our circuit so that we no longer have a closed circuit. So if this device goes out, then this device obviously is no longer on, and as a result, all other devices connected to that circuit are no longer on as well, okay? Now there's two classes of circuits that we need to talk about. The first one is a series circuit, and this is going to be our simple basic circuit. Series circuits have only one path for the electrons to travel. So that means all of the electrons are going to follow the same route no matter what. All devices receive all of the electrons and the same current. The other type of circuit that we're going to talk about is a parallel circuit. And this is a bit more complex of a setup or wiring. So this is where our devices are connected so that there's actually multiple pathways for our electrons to travel. And this is going to change how the devices are affected and how they are connected. And so this is going to cause there to be some differences in how the electrons move through that circuit or around that circuit, okay? So let's look at a diagram for a series circuit. If we have a series circuit with only one device, then it looks just like the diagram above. If we have a series circuit with multiple devices, then we need to make sure we understand what happens and how having multiple devices affects our circuit. So first, let's make sure that we recall the vocabulary word current. So current is the word for the rate of flowing electrons. All of our electrons are going to leave the positive end of our circuit, and they're going to move around the circuit until they make their way all the way back to the negative end. So my electrons would follow this pathway as they make their way around the circuit and ultimately come back to the negative end of the battery. You can see from this illustration that all of the electrons would reach all of the devices. So we would say for a series circuit that our current is constant. All of the electrons move together. They're either all moving because the circuit is closed, or they all stop because the circuit is open, okay? If we were to talk about the amount of voltage that these different devices receive, that is going to depend on the device that we have connected and how many devices we have connected. So remember that voltage is the ratio of energy per coulomb. So all of our electrons are going to come out of our device here with full cups of energy. So all of them are going to be carrying those little cups. If you think back to the notes from the other day, they all have these cups with some amount of energy in them. And what they're going to do is they're going to take that energy and they're going to pour that energy out into our electrical device so that the device can work. And so as a result of that, the amount of voltage available is going to drop or decrease, right? It's going to lose some of that voltage because that energy is being used up by our device. So as our electrons pour that energy into this first device, their cup is no longer completely full. How much voltage they lose will depend on the device itself, but they will lose some of that voltage. So when they get to that next device, their cups are no longer full. Of the energy that they have left, once again, they're going to pour some of that energy out into this device so that it can turn on. That device is going to use some of the voltage. So now their cups have even less voltage than before, but it's still not empty yet. When they get to that very last device, they're now going to dump all of the remaining energy into that last device. So our electrons are going to now have zero amount of energy left. So we say that they return to the voltage source or the battery with 0 volts remaining, okay? So I changed the colors here so you can kind of see that these are intended to represent different values. But remember, the general rule is that the voltage decreases, and sometimes we will see the word or the phrasing drops as the electrons move around the circuit. And so what has to happen is that by the time they get to their last device, the electrons will always return with 0 volts. So I could have drawn this illustration with 1 resistor. I could have drawn this illustration with 10 resistors. It's going to leave the battery fully charged, so all voltage available, return with 0 volts left, okay? The resistance value is going to vary depending upon the type of device that we have connected. We would call this our first resistor because if you look at the direction of the electrons, it's the device that the electrons encounter first. This would be our second resistor. This would be our third resistor. And this squiggly line is a generic illustration for all devices. These could represent batteries. These could represent light bulbs. These could represent your microwave, your curling iron, your blow dryer, your television, whatever type of device we have, okay? So the resistance value will depend on the device itself. If I ask you to calculate the total resistance for this circuit, you would simply add those three resistors together, and that would give you your total resistance, okay? All right, let's look at a parallel circuit now. A parallel circuit is going to be different because it is going to have the devices wired in parallel lines. Okay, so here is our voltage or our battery source, and then we would have some sort of conductive material, most likely a wire, coming out of the positive and negative end of the batteries, and then we would have wiring connecting that battery to the rest of our circuit. So for this example, we will just have two branches, and each of these branches will have one device or one resistor on that wire. Okay, so first let's start off with talking about our current once again. Our current, remember, is the flow of electrons. So all of our electrons are going to come out of this battery. They're going to flow down this wire. But because this is wired a little different, our electrons now have to split up in order to wire the entire device. So you can see that we have a branch right here where some of our electrons are going to have to choose to go down this first little wire, first little branch off, and some of the electrons are going to have to continue down that wire to the second device or second resistor, whatever that may be, okay? So for a parallel circuit, our electrons are splitting. Our current is going to now be different depending on the route that the electrons took. The remaining electrons in this example would go down that second wire, and then the electrons would both make it through the device and then ultimately make their way back to the battery, okay? So our current for a parallel circuit is a little bit different. Our current is going to vary depending upon the branch that it goes down. So each time that the wire splits, we call that a branch. And we're going to give you illustrations where you will only have one device on each of the branches, so that will keep it pretty simple for you guys, okay? So now let's talk about that voltage again. Our voltage, remember, is the ratio of energy per coulomb. So all of our electrons are going to come out with full cups of energy. So the electrons, as they travel through our circuit, are going to have these little cups, and those cups are going to be used to carry that energy through the circuit. Now, as our electrons travel down this first wire, and those that choose to come down the first branch, they have not encountered any devices yet, so they're going to have full cups. These electrons are only going to encounter one device on this branch, so what happens is that the electron is going to dump the full cup of energy into that first device. So coming out of the device, our electrons have empty cups. So right off the bat, they go from all of the voltage to 0 voltage. Why? Because all of the voltage must be used in a circuit. So this first branch, the device receives all of the voltage. So if this is a 12-volt battery over here, then that means the first resistor received 12 volts. The second branch has its own set of electrons, which currently have full cups of energy. So they come down this wire with full cups of energy. Now they are also only going to encounter one device. So all of that voltage is dumped into that second resistor. That means that these electrons are going to come out with 0 volts remaining. So if you were to be asked about what is the voltage drop or what is the voltage across resistor 1, that would be 12 volts. What is the voltage across resistor 2? What is the voltage used by resistor 2? What is the voltage drop for resistor 2? These are all ways that you can hear or read that worded. It would be 12 volts. So we say for a parallel circuit, it's the voltage that is the same for all the different parts of our circuit. Because they only experience the one resistor, they give all 12 volts to the device that they encounter. So then you can see from the illustration, they all return back with 0 volts, and that is going back to the day 1 notes. That is the main concept behind electric circuits. All the voltage is used, and they return with 0 volts on the way back to the battery. Okay. Our resistors, once again, are going to be dependent upon the type of device. So how much resistance each device provides will depend on whether it is your microwave, your blow dryer, or your TV, or whatever. So when we're asked to calculate the total resistance for a parallel circuit, it's a little bit different this time. Instead of just taking our devices and adding up the resistors, we actually have to invert those and then add them up. Okay, so your formula for your total resistance is going to be R to the -1 power is R1 to the -1 plus R2 to the -1. Now we'll do a quick little algebra review. Anything raised to the -1 power is the same as 1 over x. So whenever you get ready to do your math work over here, this is essentially 1 over x equals, and then you would have 1 over whatever those values are. We would never leave our final answer as 1 over x, right? I'll make up an answer over here, 1.234. We would never leave our answer as 1 over x. We would have to take that and flip it, right? So x would be equal to 1 over 1.234. So this concept is what you will have to apply if you're being asked to find the total resistance for a series for a parallel circuit. You're going to have to make sure that you take whatever this comes out to be, and you're going to take that answer and you're going to flip it, okay? And that is going to give you your final answer for a parallel circuit. All right, I hope this information was helpful. Just a general overview of circuits and the difference between series and parallel circuits.